Okay, so today's speaker is Frank, who's going to tell us more about TESSERA.
Okay, yeah, thanks, Kesha, for the introduction. And yeah, so I'm here again, giving the same talk, but I promise you, like, this one is different from the previous one because I have something additional for you. So this won't be an identical talk. But yes, today I'm going to talk about TESSERA. So this is a foundation model that we developed here at Cambridge, and it provides some very useful embeddings for those of you who might not be very familiar with embeddings. You can just perceive embedding as some like magical numbers. While these numbers are probably some like very useful features that you can just use it for like cross mapping for habitat mapping, whatever. Yeah, so yeah, let's just get started. So first of all, some like brief intro. So why do we want to observe our front space? Because it's super important. It helps us to monitor the biodiversity for land use and also for food security, because we can somehow estimate the crop yield. And also here's like other downstream tasks that we can do. So it's super, super important. And right now we're using satellite images, right? And also right now we have lots of this public satellite data. Let's say every day we have petabytes of data. But the thing is, most of this data, they are not fully used because some of these images they've been cloud corrupted, and also some of these images they don't have meaningful insights. That's why we're gonna need an AI model to process them. Like we cannot just use it for use this raw satellite images. But the thing is, if you want to process them, then there are some challenges in it. So let's say this is the sensitive data that we have, then I show you the GIF here. Like you can see one problem is that some of the images they have cloud. So whenever there's a cloud, then basically this observation is not usable because like cloud doesn't include any useful information. And the other thing is that if you just take a look at the time step here, well, you can see we have varying time gaps. So sometimes we have observations every week, while sometimes we have observation every 2 weeks. And sometimes if there is, if the observation is cloud corrupted, then probably we're going to have the next valid time step maybe next month. So we have this varying time. So yeah, so these are the challenges. So right now, what people or what traditional methods usually does is the so-called temporal compositing. So what people do for temporal compositing is that, let's say I just set a time frame, time window to 1 year. And what I do is like I somehow composite all the observations within this 1 year time frame, while I choose the value the cloud-free like images from this part, while the cloud-free images from that part, and I just compose them together. So the composited image will be cloud-free. But the thing is, if we're doing that, then we're losing this temporal signal, which is super, super important. So if you just take a look at the image right here, so I think the x-axis, these are the time steps. Let's say this is January the 1st, and this is the last day in December, and here these are the reflectors. Like you can see, we can simply distinguish between all these species by analyzing their like temporal signal. But if you're compositing them, then essentially you're losing all this temporal signal. So that's why we're not doing that, because this is so important. And so here, so in summary, the seasonal dynamics will help us to identify land cover and also detect these changes. So here, this is the brief pipeline or like the current paradigm to process the satellite images. So what we do is like we have this raw satellite images, and we're doing a lot of pre-processing first. So let's say, for instance, the one, which is the SAR data, that we're going to use like noise removal, and then to filter this noises, and for optical images, let's say for instance the two, we have all this correction, and for other modalities, we have this processing pipeline as well. Then after all these steps are done, what we do is like we can extract the useful feature, right? We're not using all the satellite images because that would be a huge amount of data, but we only selected the useful features among the satellite images. Then after we have these features, we use some like modeling and also further analysis that in the end we have some insights. Let's say how much crop field is there for this year, and also whether this forest is changed or not. So essentially, this is like a pipeline from the raw satellite images to the eventual like insights. So what foundation model does is I draw a bounding modes here. So basically, these are the this is how the foundation model does. Basically, just trying to wrap this thing into a black box and simplify all this process. So here, I also list a lot of like remote sensing foundation models. Actually, there are over 100 of them. So here I only analyze, a couple of them. And also, I'm doing this like taxonomy, like split them into different categories. And yeah, so we know that there are a lot of these foundation models there. And so yeah, TESSERA is also another foundation model. That means it's among all these like over 100 foundation models. But TESSERA is quite different from a lot of other foundation models because we have this character which we which we output this intermediate output that we call them as representation or the embedding. So here embedding you can just perceive it as some like numbers, while these numbers capture some of the useful features. Well, but these embeddings, they don't have physical meaning, so you cannot interpret them. It's not like, let's say we have 128 dimension embedding or the features. It doesn't mean that the first feature is corresponding to water, or the second one is corresponding to, let's say, chlorophyll. It's not like that. So we don't have physical meanings for that. And so, yeah, this is like the high level of what TESSERA does. So essentially, TESSERA just somehow compresses or processes all these satellite images into 122 dimension or 122 band image. This image doesn't have any physical meaning. It's just some like numbers, and users can just simply use this 128 band image for the further modeling and analysis and then get insights. So basically, TESSERA goes to somehow simplify all this like pipeline. Yes. And so right now we're not doing this anymore. Like you don't really need to care about the raw satellite images. You don't need to do the pre-processing, because we've done this for you. And yeah, so I'm going to talk a little bit about the methodology of the TESSERA. But first of all, I need to spend a little bit of time about talking about self-supervised learning, because TESSERA is trained in the self-supervised learning paradigm. And here, this is one of the very classical self-supervised learning algorithm. It's called a masked autoencoder. So what this method does is like, let's say we have the raw image here. What we do is like we mask, let's say 80% of the pixels, and we got a masked image. Then we just input this image into an encoder. Then after the encoder, we have some representation of this image. So essentially, representation is just like a very compact representation of this raw image. And then we fit this representation into a decoder. And what this decoder does is trying to reconstruct the raw image. Then the way we train this model is like we just simply calculate the loss, the similarity between the reconstructed image and the raw image. Then if they're very similar, then we can just, if they're not similar, then we just penalize the model. So this is how we train this model. Then finally, you can see like actually the model learns something because it can just reconstruct this image very well. Then if we can do that, then we can say this encoder must learn something because it can reconstruct it from this very noisy masked image to its original image. Then we know like, well, okay, this encoder learns something. Then we can use this encoder for some other tasks. So this is like the magic of self-supervised learning. And also you can see what distinguishes from the traditional supervised learning is that in this self-supervised learning paradigm, we don't have labels, right? All we have is the raw data. We don't have any labels in here. Let's say we just have this image. And basically we just use this raw image as the label. So this is like the difference between the self-supervised learning and the supervised learning. Okay, so Yes, becomes TESSERA. So TESSERA also uses this self-supervised learning paradigm. So what we do is like, first there is a concept. This is like the data unit that we use. So let's say these are the Sentinel-2 images, and this is the time series. Let's say we just gather all the 1 year of data. So we have this multiple observations. Then you can just perceive like there's a laser, then you just shoot a beam, then that penetrates all this time series. So each this intersection is a 10 by 10 meter pixels, right? So what we do is like we just gather. Sorry, where is my mouse? We just gather all these pixels that we reconstructed them or we reformatted them into this a new like data unit that we call them as dpixel. So essentially, dpixel is a two-dimensional matrix. What the y-axis here, these are the observation dates, right? So let's say if this is January the 1st, then this will be 1. If this is the last day of December, then this will be 365 or 366. And the x-axis here, these are the spectral, because for Sentinel-2, we use 10 bands from RGB and also infrared and also like shortwave infrared. And for Sentinel-1, we only have 2 bands. So essentially, like the y-axis, these are the time axis, and the x-axis, these are the spectral axis. And what we do for TESSERA architecture is that, let's say, so as an example, let's say this pixel is corresponding to a cone, right? So we just call it as a cone pixel. What we do is like we randomly sample along the temporal dimension. That will give us 2 augmentations from sparse temporal sample. So what it means is like this. So let's say for the augmentation up here, we select the second observation and the 7th observations. So let's say we just select a subset of all these observations. This will give us augmentation 1. And for this branch here, we do the same thing. Like let's say we select the first one of the first observation, second observation, then this will give us a subset of this cone like pixel. And you can see here, since we only do a subsampling, so essentially this dpixel is a distortion, right? Because it's not the complete dpixel, it's just a subset of that. So we also call this as cone with distortion 1, and this is cone with distortion 2. And what we do is like we input them into encoder, then we got the representation. So this representation is also a very compact representation of the raw dpixel. Then it's just like the MAE, we just input them into a projector, and then we got another embedding. This is like the a quite large embedding. Then we just calculate the loss. Then, because essentially, although these are cone with distortions, but essentially they are cone, right? So we just by simply like compare them. If they are very close, then we say, okay, the model learns something. If they're not close, we just penalize the model. So essentially, these are the core idea of TESSERA. So it's just like we're doing these 2 augmentations, then we just calculate the loss by answering whether they are the same or whether they are similar or not. This is how we train the TESSERA model. And yeah, so this is like a more formal diagram of the TESSERA like architecture. Because we use Sentinel-1, Sentinel-2 data, so we have 2 branches for each of the modality. So let's just take a look at Sentinel-2 branch. So what we do is like we extracted the dpixels, right? So these are the dpixels. We have 2 dimensions, time dimension and the spectral dimensions. Then what we do is, and also one note is that some of the observations, they are cloud corrupted, right? So when doing the sampling, we're not going to choose all this cloud corrupted one, we just get rid of them. Then we have these 2 augmentations, send it into encoder, get the representation, and then through a projection, this is basically to enlarge the dimension of the representation. Then we just calculate the loss. So for Sentinel-1, this is the same thing, but since we use 2 different modalities. So here, after we have this Sentinel-2 representation and also the Sentinel-1 representation, we're going to use a very small model to fuse them. So essentially, this is like a future fusing. And then, yeah, so this is it. This is everything about TESSERA. So it's quite simple. And so this is a summary. what TESSERA does is like we provide this ready-to-use representations because right now users they don't need to deal with the raw satellite images anymore. Right now they just use our representation as their data. So this is what we call it as embedding as data paradigm. So we provide ready-to-use representation, and also we encode the spectral like the temporal signals in these embeddings because we're not doing compositing. We still keep the temporal information. So these embeddings they are spatial. Also, sorry, they are temporal and spectral aware. And we're doing sensor fusion because we're using Sentinel-2 and Sentinel-1, and also the resolution is 10 meters. And also we can publish the global data set. So that means everywhere on Earth, every 10 by 10 pixel on Earth will have a corresponding TESSERA like embedding. And also everything is open source. So yeah. So
everywhere on Earth except the water, maybe the ocean.
oh yeah, sorry. So we only provide the TESSERA embeddings for the land mass. So we're not providing the embedding for the water because I think water is basically the same, right? Like the reflectance is the same. Yeah. So here, these are the most interesting part, I think. I mean, yeah, so we have this 122 embeddings, but this is how they look like. But here I only use the first 3 channels since the embedding have 128 channels. So I just select the first 3 channels. And you can see how colorful they are. Yeah. And also, so we're not the first remote sensing foundation model that provides this embedding. Actually, Google's Alpha Earth is one step ahead of us. So like Alpha Earth is like the elephant in the room. So here I have to compare Alpha Earth against the TESSERA one. So here I just choose this is a place near Vienna. This is a crop field. And if you just zoom in, you can see here. So if you just take a look, so first, obviously, like TESSERA is more colorful than Alpha Earth because you can see like we have. So usually, like more colorful means that it contains more information, right? And also, if you just zoom in here, you can see there are some like this square-like artifacts on the Alpha Earth embedding. That is because they use this patchwise like methods to generate these embeddings. So they have this like cropping artifacts here everywhere basically. But since we're doing in a pixel-wise way, right? So we're not having this patch like artifacts. So this is like one of the strengths that we have compared to Alpha Earth. And also here, this is like a more comprehensive comparison. So first of all, TESSERA only uses Sentinel-1, Sentinel-2, and Alpha Earth actually uses a lot of data. So the inputs of their model is Sentinel-1, Sentinel-2, and also Landsat. But they use some like very strange modality, let's say text and also JEDI and also DEM, something like that, in their training pipeline as well. But so TESSERA is quite simple. We only use Sentinel-1, Sentinel-2, and also for coverage, we both want to achieve global coverage from 2017 to 2024. But I have an error stack here because right now we haven't achieved that. So we're still trying really hard to achieve this goal. But because they're Google, so they've done this before. So they have already achieved this. But yeah, we're trying really hard. And also for the embedding dimension, we have 128 while Google has 64. But our embedding is in integer 8, while their embedding is float 64. So essentially we have, although we have more bands, but actually the storage that TESSERA embedding requires is less than that of Alpha Earth. And the time granularity is both NU and resolution is the same. And also, like I mentioned before, we adopt a different methodology. So TESSERA is a pixel-wise foundation model, while Google is patch-wise. And it's open source. And so in terms of open source, TESSERA is fully open source. While Google only like publish the annual embeddings they have, they don't really actually release the model, like also the training script. So we cannot know, we cannot basically reproduce their model. So here it is marketed as partial. In terms of license, we have very flexible license. Well, I have no idea what Google's license is. Yeah, so this is basically, so next thing is how well does this embeddings work? We evaluate TESSERA and also its embedding on a variety of different downstream tasks. So the first one that we evaluated is the crop classification task. This is a crop data set we have. This is somewhere in Vienna. And one thing to emphasize that is this data set is a little bit unbalanced. So there is winter green here. This is like the predominant class, while you can see there are some like, let's say grapes and tree fruits. These are underrepresented in this data set. So actually, TESSERA performed super good on this data set. So so the y-axis, these are the F1 score, while the x-axis, these are the labels that we use. Let's say 0.01 means we only use 1% labels, while 0.3 means we use 30% of labels. So this purple line is TESSERA. Also here, this is TESSERA. While this orange and this reddish line, these are the these are the baseline. That means we use the raw Sentinel-1, Sentinel-2 images together with the random forest. This is like very traditional baseline. While actually Google is down here. So this green one, this is Google. And also we evaluated another foundation model as well, which is called Presto. So Presto is comparable to Google, but Presto is like this blue line here. Yeah, so this figure A and C, these are like the performance of different like foundation models, TESSERA, Presto, like Alpha Earth, and also the baseline. Yes, so this is a pixel-wise crop classification. We also evaluated on the patch-wise segmentation task, where this is the data split like strategy. So these are for validation, this is for testing. And also each patch is 64 by 64. These are the results we have. Actually, here I evaluated more remote sensing foundation models. So we have DOFA, remote clip. These are actually very, very famous foundation models in remote sensing. And TESSERA is here. You can see, so 1% means we only use 1% of patches. 30% means, the 100% means we use all the training patches. So TESSERA can achieve 53 so this matrix is, I think, intersection over union, which is like the very popular matrix when evaluating the model in segmentation tests. So TESSERA can achieve 53, which is, I think, far beyond all other foundation models, and also even under very limited like data, training data, let's say 1%, we can still achieve 28. So yeah, this is really good on crop classification test. And here, this is another test that we did. So essentially, we're just trying to predict the canopy height. This is somewhere in Malaysia. So what we did is like I mentioned before, you can just perceive TESSERA as an image. It's just like this image has 128 channels. So what we did is like we input this image into a unit, which is like a spatial information extractor. Then we're just trying to map this embeddings to the ground truth like height, and this height are from LiDAR data. And these are some like results that we have. Let's say if this is a ground truth, then this is a prediction. I mean, visually, they look very, very similar, right? And here, this is like a results that we analyze. So TESSERA can achieve over 0.6 on this canopy height like prediction test. So here we have some other comparisons as well. This is TESSERA, R square is 0.66. This is Presto, another foundation model, it's like 0.5, and this is actually Alpha Earth. So it's relatively poor because it's basically below 0.4. And these are other like products that we compare against. Oh, this is another task. And this is not done by me, this is Yovna's work. So yeah, so I mean, if you just take, I think figure 1 is pretty interesting. So you just take a look at figure 1. This is a UMAP that we did. So what UMAP does is like, these embeddings, they are 128 dimension, right? So we just reduce the dimension to 2. That means from 128 to 2 dimensions. Then we just draw all these pixels into in this like XY plane. And you can see here, TESSERA embeddings, they can actually not only tell like whether there is a fire or not. You can also tell like when the fire happens. So this is June fine, this is August fine, and this is the unburdened area. And also what's interesting is like, if you just take a look at the August fire, I mean, the cluster, the little cluster here, you can see there is a obvious, like very obvious gradient, like from low fire severity to like moderate, like fire severity and also too high. So that means like these embeddings contain a lot of like useful temporal information as well as the semantic information. Yes. All right, so just some like more downstream tasks. I think I'm gonna skip that because I have like more slides to show you. So this is another downstream task that we use for predicting the above ground biomass. And the key takeaway is that TESSERA performs very good. It's at least it's better than Google. Yeah, this is like another land use change detection. This is not in the paper, so this is just for fun. Like I just draw the embedding map for Cambridge from 2017 to 2024, and this is London. This is how like these two different places change in the embedding space. And so here, this is a very rough change detection. And so basically, I just calculate the cosine similarity between the two adjacent here in the embedding space. And I just set a threshold to select all these places that might experience a change, but this is not. I didn't really validate this with the ground truth data. So I'm not quite sure if this are right, but yeah. Okay, so actually we have done this for other downstream tasks as well. So you can see like the red radar plot. This is TESSERA, while all these are inside. These are other foundation models. Yeah, so these are some like additional work that I've done recently. So one is like cloud robustness, because we use this in SINCEL2, and we know that SINCEL2 can be cloud corrupted, right? Like I mentioned before, if SINCEL2 images, if it's cloud corrupted, then basically we cannot use that, right? Well, the thing is, so here I just analyze the valid SINCEL2 observation across the world. So valid here means it's not cloud erupted, it's not water, and it's not snow. It's not snow. And here this is for 2024. And here if the valid observation is below 10, then I just use this like blue tile. And yeah, so if it's like over 40, then these are the red. Like you can see, I mean, in most of the places, I think the value of observations for SINCEL2 is, I think it's over 20, right? But still we have some places, maybe some here in Europe, we only have like 10 to 20 like valid SINCEL2 observations. And here, this is for other years as well. So from 2017 to 2024, and you can see, actually 2017 is quite outstanding from all these other years, because you can see, especially in the Amazon region, we have very few valid SINCEL2 observations, basically below 10, right? And also here, probably in Asia, and also this, I think this is Tibet. We have.
Just wanted to see Africa in the is that blue area? Is that Gabon?
Yeah.
Yes.
Okay.
Yes. Yes. So yeah, this is the cloud like status for SINCEL2. I mean, the problem is like TESSERA uses SINCEL2 as data sources, but what if a place that have very few like SINCEL2 observations? But I mean, if that happens, then how would it impact or affect the TESSERA embedding? So what I did is I do an analysis. So the y-axis, this is a down on Austrian crop data set. So the y-axis here, these are the F1 score. It's just like the matrix, the higher the better. And the x, this is the max SINCEL2 observation that we use. So let's say if we use 60 like observations, then TESSERA can achieve 0.77. This is pretty good. And also here, I also draw the average valid pixel ratio. That means, so if this is 1, then basically it means that it's all cloud free. If this is 0, then it means like most of the observations, they are cloud corrupted. So this is an analysis. I can see if we just keep decreasing the number of SINCEL2 observations, I think above 20 is okay, because it drops from 77 to 69 or nearly 70. This is quite steady drop. But if the observation is 10, let's say below 20, then there is a significant drop, like to 0.56. And if you just keep decreasing the number of sensitive observation, then basically it's just not working. Like it's just like 41 to 32 to 27. Basically, it's not working. So yeah, so that means that if a place that has at least 20 sensitive observation, then basically tessera embedding is trustworthy. Also, one note is that these are not valid sensitive observation. These are just max sensitive observation. So whether it's cloud or whether it's cloudy or it's cloud free. So yeah. So this is that means like cloud this tessera embeddings, they're quite robust to the cloudiness. And another thing that I did for tessera recently, actually this is not recent, it's a long time ago. So yeah, so tessera is actually quite large, and we use a lot of like GPU resources to train them. So it is trained on AMD MI300X, which is quite beefy GPU, and also trained it for 6,000 GPU hours. So here, what I did here is to answer the question. So what if we have more GPUs? Let's say, what if we are Google? Like how far can we go? So the picture A here, this is y-axis. This is the width. This is the width of the model. So you can just perceive the model as a rectangle. Like maybe like the wider it is, the more parameters it contains. Also for depth, this is essentially the same. So if we just go all the way down to this corner, then the model gets bigger and bigger. Let's say the biggest one here, it's almost like 10 billion parameters. And actually the final model that we use is here. So this like star one here, this is the tessera version 1 model. I think it has 1.4 billion parameters. But you can just clearly see that if we just keep adding more stuff, let's say if we just enlarge the width and also enlarge the depth, actually the performance will keep going up, right? Because the performance is here. This is a validation of one score. I mean, if it's close to yellow, then the performance is better. But here, so right now we are here because we don't really have too many GPUs to use. But so this is like yes, this is where we are. And for figure B, this is another test. So the x-axis, this is the training flops. You can just perceive it as like how long it trains. So you can just ignore these flops. You can just perceive it as, let's say, training time. So this x-axis is training time, while the y-axis, this is the model size. Like if the model is getting very large, then it goes up here. So we're at this stage. So this is tessera version 1, where we train it for 6,000 GPU hours, and then this model is 1.4 billion. But so here I just draw some like contours here. Like you see, we can actually draw a line somewhere here. So basically it just means that if we just keep like enlarging the size of the model, and also if we train it like longer, then we can just anticipate that the performance will keep going up. Because I think probably like this one. So we can just draw a line here. So probably will go that way. So that means like if we have more GPUs, actually we can make tessera much more powerful. And yes, these are more event maps. I really enjoy looking at this because this is really useful. So here is to compare tessera against Alpha Earth and also against Presto. And you can see for Austrian crop, it's really like colorful and also Borneo. This is a data set from Malaysia, and also yeah, these are some like patches. Yes, so basically that's everything like about tessera, like in terms of methodology and also the results that we have. But actually, I think what's more exciting about tessera project is that we provide this tooling kit to facilitate the users to easily get access to tessera and also to try out, to play with these embeddings. So we basically will have 3 repos at the moment. The first is the tessera main repo. And so in this repo, we have open source basically everything. You can find the training script there. You can find the code to evaluate the model, and also you can use this repo to create embeddings yourself. So if you just want to reproduce our results, you just go to this one. And here, GeoTessera, I think this is like the most powerful repo that we have, because GeoTessera hosted all the pre-computed embeddings. So that means, let's say if the user, they don't want to create embeddings themselves, then they can just simply go to GeoTESSERA, just specify your region of interest and also specify the year. Then they can just pull down the embeddings for that region for the year very easily. This is not done by me actually. So this is Anil's work. Anil spent a lot of efforts in this GeoTESSERA repo. And the third one, this is done by Robin. So Robin just created this very useful interactive map. So basically, this is just a Jupyter notebook. So where you can just draw a bounding box, select your region of interest, and it will just visualize the embeddings of this region. Then you can just add some, let's say if you want to do classic like land classification, you can just add some labels. Let's say these are water, these are urban. Then you just simply click classify. Then the Jupyter notebook will tell you, well, what is the classification results for this region. So these are really, really good tools if you want to play with TESSERA and also TESSERA embeddings. And yes, so this is how GeoTESSERA works, right? Like I mentioned before, you just specify the bounding box and also the year. Then the GeoTESSERA will query from our embedding database, and you can just get this TESSERA embedding, which is a H by W by C. And you just input into a very simple model, let's say NLP or random forest, whatever. They can just do any other downstream task, classification, segmentation, regression, whatever. Yeah, so this is one example that I did, I think, probably last month. So let's say right now we want to track all the farm PV panels in the UK. Actually, it only takes me 2 hours to do this. So I'm gonna show you how to do this. So the first step that you need to do is you go to the GeoTESSERA repo. And it only takes me 1 minute because you need to check if the embeddings are available for the region. So here for the whole UK, you can see this is green. So green means that we have all the embeddings from 2017 to 2024. So that means I can do this because we have embeddings here. Then the second step is I just download all the embeddings. Actually, this is the most time-consuming part because it takes me basically 1 hour to put down all these embeddings for the whole UK. And the third step is I create some PV panels myself. So I just go to Earth Engine or QGIS or whatever tool that you're using. I just manually label some of this PV panels. And also I did this only for 2024. So yes, and it only takes me 50 minutes to do so. Then I just ask Claude to give me a pipeline for pixel-wise PV panel detection. Claude is doing a really good job. It only takes 10 minutes. Then I just train XGBoost model. You can also train a random forest or whatever model. And since I only have this very few labels, so the training only takes for 1 minute. Then I have the model. So right now I need to use this model to track all the farm panels in the UK. So what I do is I just use this model to do the inference for the UK from 2017 to 2024. And the inference takes a little bit longer because we're doing it for the whole UK across 8 years. And so these are all the time that I spent. Basically, it's less than 2 hours. And so how does the result look good? Yes, actually, it looks very good. So if you just take a look at the left side, this is a global data set from one of the literatures. And you can see I highlight this using this circles. And these are the PV panels detected by TESSERA. And you can see actually we're doing a better job comparing to this global data set. I mean, obviously there are some panels that this global data set doesn't, detect it, right? So, but actually TESSERA is doing really good. And also one thing to mention is that these two outputs are actually from 2022, but actually we only use 2024 embeddings to train the model. So that means TESSERA embedding have very good transferability across the years, right? Because we only train for 2024, but we can do for 2020 as well. And also in terms of the geolocation, locational transferability, I did another test. So when I created this PV panel ground truth data, I think I just pick a random place near London. I think to west of London. But then, so this is a place in Scotland, and these are the inference from 2017 to 2024, and you can see actually before 2024. It's quite stable, right? So we know that, well, this place has a PV panel. But then after 2024, we see there are some new panels popping out. So I just go to the Google Earth and just check that. Well, this is true. This is not a mistake. So indeed, in 2024, there are more PV panels installed. And also, this place is from Scotland, so we don't have data training there. But that means because we only use data near London for training, but still, like the model can generate to Scotland. So yeah, this is super cool. And I think this is probably like the end to like the end of this talk. And right now we're still seeking collaborators. I mean both external and internal. So if you're a Cambridge user, and of course I can prioritize your like our collaboration. And yeah, so these are the link to our paper and also to our Python library. And if you're interested, you can just scan this QR code. Also, I think one thing that I want to ask is that if you find the GeoTESSERA library useful, you can just give us a star. Right now we have, I think, nearly 400 stars for our GitHub repo. But yes, I think that's the end of this talk. And yes, thank you.
Okay, go ahead.
Yes, yes.
I'm interested in the cloud experiments that you did. Did you do uniform dropping, like uniform sampling, when you drop the number artificially simulated cloud coverage?
I just drop random.
Yeah, because I feel like I'm not an expert in like signal processing, so someone who is, but I think if you do like uniform dropping,
Yes.
you often can reconstruct the signal perfectly. And often I think for clouds especially, they're seasonal.
Yes.
And so I definitely think if we want to do like a more realistic cloud robustness experiment, we should do like clustering. So drop seasons, drop whole months, things, because I'm assuming like, yeah, we're kind of sampling, but as long as it can kind of infer the curve, it's probably still doing a pretty good job, especially for Austrian crop data set. Yeah,
I see. Yeah, that makes sense.
Yeah.
I have one question and one thought. My question is that based on the data you use and the way you train TESSERA, like the Barlow Twins architecture, do you have a rough idea of what kind of downstream task it will perform particularly well, and any downstream task you think it won't perform very well?
Well, since the TESSERA, like the training, so we use the Austrian crop data set to somehow monitor the training, right? So we selected the best weights according to the results on the Austrian crop data set. So I think somehow the model is towards the crop classification. So I would say if the downstream task is called the crop classification, then TESSERA will perform like surprisingly well. And for other tasks that TESSERA might not require, actually I have no idea. Like,
but it does canopy height as well, much better than Alpha Earth. So that's a structural one.
Oh yeah.
Right.
Yeah.
But for example, for habitat classification, it was kind of on par. So
Yeah.
I don't know.
Yeah, and sorry, I have another thought.
Yeah.
You mentioned a plot about like the model parameter, the size of your model and the time it required to train. I want to ask, do you train the model from scratch? And
yes, this is trained from scratch.
I have a thought, like if you think like someone has trained a model, let's say not for remote sensing, but they have a vision foundation model,
Yes.
like Dino V2.
Yes.
Or if Google has released its model like Alpha Earth, but can you use their feature backbone and use something like the low rank adaptation technique to like which you can still use your architecture and your training like loss function, but you can borrow their feature extractors and then adapt some component that is reusable.
Yeah, I think that makes sense. I mean, it's quite usable. I mean, it's like a common practice for a lot of tasks. But the thing is, I think the difficulty of doing that is like TESSERA is totally pixel based. So that means all its embedding or its features, they are pixel based, while all other foundation models basically they are patch based. So it's really hard to like adjust the patch based like features to this pixel. So it's really hard to align them. So I think, I mean, theoretically it should work, but I think it's more like an engineering challenge, I think. Yeah. But then thanks for the suggestion.
Do you know what it means with the firstly, it's a fantastic talk. I think I've heard several of these talks now, but that was the best yet. So every time I hear them, they're slightly better than the script. Do you know what this patch-based learning, the Google Earth Alpha Earth is actually doing? I mean, and I was just wondering about the temporal normalization issues, which Google has seen when we're looking at a change over time. That Google Alpha Earth is embedding are super stable over time for intact forests, whereas the TESSERA ones are jumping around in space. And so is it something to do with that, the patchiness of the Google embedding?
I think I mean I just took a look. I think I read the Google paper twice, but I think I still don't really know like what are the details of training their model. But I think the reason why, I mean, yeah, if they're doing patch based, then probably something gets smoothed out. So I think that's probably the reason why Google Alpha Earth embedding they have better, like comparability again, like between two adjacent years, especially for 2017, where most of the cloud is happening in 2017. I think that is one reason. Another reason is that since TESSERA always use 40 time steps, right? And we know that in 2017, there are far less than 40 valid time steps in Sentinel-2. So I think that is why TESSERA embeddings, they have relatively poor comparability between 2017 embedding and also 2018 embedding, because we don't have many observations here. But I think what Alpha Earth does is that they don't really use that many observations. As far as I can tell, they probably only use like, let's say 10 valid observations. And these observations, they are cloud free. So they will not include any like cloud corrupted patches into their training. So I think that's probably the reason why they have this like smoother like embedding across years. Yeah.
Really awesome talk and awesome works, I think.
Thank you.
I'm interested about the cloud stuff as well. So with the Austrian classification, when you reduce the number of observations like under 10 or whatever it wasn't,
yes,
performance wasn't great. As an end user, say like I knew nothing about this and I wanted to train a model, use it in Gabon, but it's like no observations. How would is it easy to pull out the information that it's likely to not work well there because there are few observations? Like, is that information released along with the embeddings? Like, okay, at this pixel there weren't any valid observations, so you probably shouldn't trust it as much.
Yeah, I think we will probably give user a notice when, let's say for Gabon, because Gabon has let's say less than 10 observations.
Yeah,
I mean, right now I don't have any like I don't really evaluate the embeddings for the Gabon region. But I think this is somehow similar, right?
It's a quality flag.
Yeah, I think it's like quality. Like, I would assume that actually the embedding quality in Gabon will be much poorer than, let's say, the places where I have more sensitive observations.
I think it's a good point. We really probably should be putting a quality flag, or maybe not in a flag, just a metric saying how many observations you used.
Yes.
And if you have very few, then basically buyer beware.
Yeah.
Because I wouldn't discount completely. Yeah, it's better if you just say the number of observations, because in Gabon in general, whoever wants to use optical sensors, they're gonna have this problem. So they can then just compare, oh, I have this bad data and this bad data, and which one's better?
Is that information stored though, like for every pixel?
Yes, it's stored.
It's there.
It's stored, but you need to ask Frank to get that at the moment.
Let's take a question online. Ethan?
Hi, can you hear me?
Yeah.
Okay, yeah, great. So I have two questions. One is also about the cloud. So I was wondering, the cloud robustness test, was it done on using only Sentinel-2 or also Sentinel-2 and the full set of Sentinel-1 for training? And so I was wondering if it could be possible to kind of see like how much Sentinel-1 could somehow rescue the lack of Sentinel-2. Like, does it matter that if you have more Sentinel-1 for a certain location, you can have fewer Sentinel-2? I guess like because Sentinel-1 doesn't have cloud occlusion, so it will always have all of them available. But yeah, I was just wondering how much does the information in one source cover for the other? So that's my first question. And the second question is about a kind of like a practical sense. So if we have labels that are not point labels but like polygons, what would you suggest to be the best way of using that for classification tasks? Would it be better to sample points within each polygon to create point labels, or is it better to kind of aggregate the embeddings within each polygon to get one kind of embedding vector per polygon and then do the training?
Okay, yeah, thanks for your both questions. So the first one, actually, this is something I'm doing at the moment. So first, this test, I mean, this figure, for Sentinel-1, we're using the full set of Sentinel-1 observation. I think for Austrian crop, we have, for this year, 2022, we have, I think, over 80 Sentinel-1 observations. So here for this test, we just keep Sentinel-1 as it is. That means we use a full set of Sentinel-1. And so, yeah, so only Sentinel-2 images observations are reduced for this test. And also, regarding your thought, actually, this is something I'm doing at the moment. That, let's say, because we know that although Sentinel-1 will not be corrupted by cloud, but we know that some places on Earth, they have fewer Sentinel-1 observations than other places, right? So some places, they don't even have Sentinel-1 observations. So that's something I need to do next. Let's say if we just take two factors into account, so cloudiness, which is gonna affect Sentinel-2, and also to the, let's say, scarcity of Sentinel-1, where some places they don't have many Sentinel-1. So this is something I'm going to do next. And the second question, so this is actually pretty similar to what I did for the Austrian crop. So this Austrian crop, these are actually polygons. So yeah, so what I did for Austrian crop data set is that I just use all the embeddings that are corresponding to these polygons. So that means each polygons, they have multiple pixels, right? So probably like this polygon, they have like 1,000 pixels. So I just use that, I aggregate all of them into like pixel level training data. So this is what I do for Austrian crop. And also alternatively, what you can do is like, if you can just refer to this patch-wise segmentation, where you just create some patches, right? So create some patches in your polygon. Then you just created this 64 by 64 embedding patches. That means like the shape of these patches will be 64 by 64 by 128. Then once you have these patches, what you can do is like, you can just put them into a spatial model, let's say a UNet, for like spatial feature like extraction, something like that. So there are two ways they can do. So either you just aggregate them, you just extract all the pixel level embeddings. Then the second thing, you just create some like patches like this. And then, yeah, so these are the two alternatives that you can have.
Okay, thank you very much. Yeah, and the
Okay,
first
yeah.
about the first. Oh, sorry. Yeah, I was just thinking about the first point you raised about Sentinel-1 being unavailable in some places. I guess that also reflects the fact that in places with steep slopes, Sentinel-1, I guess radar data are much less reliable. So yeah, I guess that could be a way to test how we should handle those cases.
Yeah, I think that is something that we need to take into account. But I think probably we're gonna defer it to future work. Yeah, but thanks for that.
Yeah, go ahead.
I'm wondering about places that changes radically throughout the year. For instance, the crop farm that become a solar panel.
Yes.
In the model, because you're like sampling at different time, you have mixed solar panel crop, at least for the first year. How does this affect, like, the embedding should be a bit different than the solar panel one of
Yes.
the crop? Oh.
Well, we haven't really fully tested that, but let's just say, take an example. Let's say maybe like before June, this place is still crop field. Then after June, there is a solar panel installed there. Then I would assume that this place, the embedding for this place, is composed of two types of embedding. So it's like half crop and half like PV panels. I think it can be perceived like this way, because given how we do the inference. Yeah.
I mean, we did something similar, the fire UMAP that we're doing, that's on just for that one single year. These all of these pixels, the ones that are burned, they were unburned before August. Then in August, they transitioned to the burned pixel. So you can imagine that they would have looked like unburned the year prior. And then they separate. Now it's probably what would happen a year later. They might then be in a separate, separate cluster on its own.
So is it why we have like the June and August separate cluster?
Yeah, I mean, two fires separated separately. We were speculating that it's because of the timing, so June and August, and that's somehow being encoded. It could also be these are two separate fires, so maybe there's something different underlying. I don't know. It was so kind of nice that June and August separated. So it could be that it's somehow encoding the exact timing of a disturbance or proportion, but we don't know yet.
Any other questions?
I'm interested about the 64-dimensional int H versus 128-dimensional plus 64.
Yes.
The design decisions then, what do you think, how that affects them?
So yeah, in terms of like dimension, number of dimensions, obviously the larger the better, right? So right now the bottleneck is 128 for tessera embedding. I can always enlarge it to 256. Actually, I tested it before. So if you just increase the number of channels from 128 to 256, actually you have a performance boost. But it's not too much. It's like very marginal boost. So there is like a trade-off. But if you increase the number of channels, then your requirement for storage doubles, right? So there is always a like trade-off. And 128 is like a sweet point, yes.
And on the int H versus float 64?
Yes, integer 8, this is still the same thing. So integer 8 has lower precision than float 64. But we just find that originally the embedding is in float 32. So float 32 is really good. Then we just try to quantize it from float 32 to integer 4. Then by doing this, of course, we're gonna lose a lot of like precision. But we find that actually the drop on Austrian crop data set is very minor. Like it's just negligible. So but if you're just doing that, then basically just reduce your requirement for storage 4 times, right? From 32 to 8. So still, this is like a trade-off between the storage it requires and also the performance that we want. But yeah, so 128 under float, under integer 8 is like the best option.
I think one limitation here is that everything is done with Austrian crop data set. In some sense, we can't look at 10 different parameter downstream tasks and then do everything. So we had to pick one task just because of the computation load that proposes. And we picked this one, we can go into the reasons why, but there is definitely, as Frank said, there is a possibility that, we are vegetation oriented, crop oriented, rather than if you have different tasks that you would pick all these parameters for, you might end up with something a little bit better for different others. I think Ihan also pointed this out. So there's definitely a limitation, but in the end, we have theory, but then we also have limitations of what we can actually do with the tools that we have. And this is where we're at. We are at time, so let me bring this to an end. So thanks again, Frank. Okay, and we'll stop here. Thank you all.